So far we've built the video fundamentals and borders on sheet 1, the flip logic on sheet 4, and the paddle on sheet 2. Our breadboard is laid out like legacy boards, but with the chips rotated for compactness. This is kind of rough because of shared gates, but so far we've built the oscillator and clock divider, the video counters, the video mixer and composite output, the flip logic, and the paddle. Crazy. Today we'll go back to sheet 1 and work on the ball counters and ball motion controls. Let's just start with these ball motion counters. We'll need 4 more 74161 binary counters in Charlie 7, Charlie 8, Baker 7, and Baker 8. We'll use 2 3-input AND gates from Dog 7, and we'll need a new 7400 quad NAND gate in Dog 8. I said previously that the ball counters are basically a copy of the video counters, where the X counters track the ball position horizontally and the Y counters track vertically in a normal screen orientation. The ball counters run independently from the video counters, however, so that the ball location can drift per the motion controls. We showed in part 5 how the horizontal and vertical video counters skip 4 steps each frame, so that the ball counters can be biased above and below 4 to create motion in all directions. If we set both ball load inputs to 4, the ball should not move because the ball counters will match the video counters exactly. The ball motion logic should therefore never present 4s as load values. I made a list of the 8 possible load values for each axis. We know that a load of 4 matches the video counters and the ball should freeze. Let's think about this with the x-axis first. If we load values less than 4, the ball should move right because we have to take more steps than the video counters in one frame. If we load values greater than 4, the ball should move left because we take less steps. If we load a 5, for instance, the X counters take 1 less step, so the ball should move left by 1 pixel per frame, or about 60 pixels per second. If we load a 6, the ball should move left by 2 pixels per frame, and a 7 should move the ball 3 pixels per frame, or about 180 pixels per second. Since there are 172 pixels between the paddle and top boundary, it should take slightly less than 1 second for that trip. Similarly, loading a 3, 2, or 1 will cause the ball to move to the right by 1, 2, or 3 pixels per frame. We do have this 0 here, which should make the ball move to the right by 4 pixels per frame. But they don't use it because they've already got a nice balanced 3 speeds in each direction. Naturally, we're going to test that. Now the y-axis bias values are similar. Loads less than 4 take longer than the vertical count, so the ball will move down, and loading values greater than 4 moves the ball up. You'll notice that we have y0, 1, and 2, but cx0, 1, and 2. This is once again most likely due to a modification to the original design. I believe the prototype motion control logic was a lot simpler than this, probably just 1 speed in each direction. The production version has logic for speed up, different paddle reflection angles, and cocktail model support. We'll see these later if we survive this part. Let's see how these counters are hooked up. Just like before, these are synchronous, so the clock goes to all counters at the same time, and stepping is enabled via the CE inputs. The low order X counter is enabled all the time, so it steps every clock. When it reaches all 1s, TC turns on, allowing the high order X counter to step at the rise of the next clock. When the X counters hit 255, the low order Y counter is allowed to step, and when the low order Y counter hits 15, the high order Y counter is allowed to step. When all counters hit max, PE drops, loading fresh bias values into both low order counters at the rise of the next clock. Then the whole cycle starts again each frame. Let's quickly map out how the ball is displayed at the end of a cycle. We'll leave the video counters alone at the top and left, and use the bottom and right margins for the X and Y counters respectively. I'll put up random counter positions for both and we'll see what happens. All of these signals must be on for the ball line to rise, so let's walk through this starting with the Y-axis signals. The high order Y counter TC must be on, and this happens when the counter is at all ones and the CET line is high. Then Y4 and Y8 must be high, so the ball will be somewhere along this horizontal plane and be 4 lines high as they point out in the schematic. For the X-axis, the high-order TC must be on to enable gating the high-order YTC, so this counter must be all ones. The X2 and X4 signals must also be high, but this occurs in 2 places. The trick to picking one of these is that the X8 signal enables CET on the high-order chip, narrowing the selection to this area and making the paddle 2 pixels wide. In all of these counters, both CEP and CET must be high to count, but only CET must be high for the TC output to turn on. Let's hardwire the load values to 4 and turn this on. This ball signal goes through a bunch of other crap, but for now we'll just hook it up to the video bus using a spare 3-input AND gate to keep it out of the sinks. If it happens to land somewhere within the sinks after power on, we won't see it. Well, no ball. I'll poke the high order resets to get some random value. Okay, there it is. Not moving as predicted. Let's raise just CX0 to give us a bias of 5. Should drift left. Yep. Let's try a 6. Faster. And a 7. Fasterest. And yes, fasterest is another valid technical term. To make it go the other way, we need to make the bias less than 4. Let's try 3. 2. Medium. 1. Fast. And our illegal 0. Really fast. We should figure out a way to use that as a difficulty feature. Let's stop the X motion and try the same tests on the Y. We'll set it to 5, move slowly up, try 6, and pukes. I shouldn't do that. Well, after poking around on the scope a bit, the clock line looks fine, even after a long trip. You can see here, however, that the load line looks pretty crappy. Probably not adhering to hold time for that line and gets into spiraling death. Maybe similar to some of the video issues Gary Waters ran into, where things are designed right on the edge. Breadboard is not always a great environment, and signals can get dirty. I noticed that if I stick a .001 mic cap on any of these lines, the issue cleans up. This cap delays the signal a bit. You could also use a spare gate or two to delay this, but I'll just leave that in for now and do some digging offline so we can continue. So now the 6 works, and the 7. Reverse direction with a 3. Then 2. 1. And let's try out that 0. That's pretty fast. I want to have a little fun and do our own cheap motion control before continuing. I'll break out my PoorCAD. Don't tell anyone, but this is an illegal copy. I think it's version 2000 BC. To make this test simple, if we use medium speed, then we just need to change X2 or Y2 to reverse that axis's direction. We'll use a spare 7474 and a 7400. We'll hook X2 here, so when set, the ball will move left, and when reset, the ball will move right. Next, we'll check when the ball hits the paddle and set the latch. And when the ball hits the top boundary, we'll reset. And we'll do the same for the y-axis using the left and right boundary signals. I jumpered this up here. Let's pull this line for medium speed and hook X2 to the flip-flop output. Well, it changed direction. I need to turn on attract mode to give us a full paddle. And bam, bouncy. Stop that. Let's try that out on the Y. Pull this line for medium speed to connect Y2 to the flip-flop. Bouncy. Turn back on X control. And we've got a bouncy ball that plays in our box. And we do like bouncy. Pretty cool. The real circuitry is more complex than this, but at least you get the idea. Let's rip that out and keep building. Oh, wait. Thought of something. Turn off attract mode. Nice. Alright, time to work on their ball motion logic. Once again, we're using the updated RevFX schematics because the ones in the manual don't match the RevF board exactly. See Part 2 or the differences document in GitHub for details. We'll break this up into 4 sections. We have the X motion control, the Y motion control, this volley counter, and this speed up circuit. We'll start with X motion. We'll need new 7400s in Able 5 and Baker 6, a new 7474 in Dog 5, new 7486s in Charlie 6 and Charlie 4. We'll use a NAND gate from Charlie 3 and one more AND gate from Easy 5. This looks a lot like our own cheap X motion control with a few features. When the ball hits the paddle, it sets the latch, and when the ball hits the top boundary, it resets. Interesting that they use the raw ball signal here, but the synchronized ball signal here. They also reset the latch when the ball is served. This assures that the ball initially moves towards the player. SBD comes from the game state logic, which we haven't built yet, so we'll need to poke this puppy by hand. Well, actually, we can temporarily hook it to the serve switch on our control board. An additional feature of the real control is that they reverse the ball direction when a brick is hit. The brick hit signal is used as a clock, and the data input is hooked to the inverted output. This is the typical wiring configuration for a flip-flop or divide by 2 circuit where the output inverts with the rise of each clock. In this setup, no matter which X direction the ball is traveling, hitting a brick will reverse it. So hitting a brick from the front will send the ball back towards the player, and hitting a brick from the back after a breakthrough will cause the ball to bounce towards the top boundary. The brick hit signal comes from the brick logic, which we haven't built yet. So we'll throw up our own fake brick wall and generate our own brick hit signal to test this out. Just like in our cheap control, When the Q output is high, the ball moves towards the top boundary, and when the Q output is low, the ball moves towards the player. These two exclusive OR gates flip the ball direction when player 2 is up on a cocktail table model. When player 2 conditional is off, we can think of these gates as simple pass-throughs. And this other gate helps generate the proper X counter bias values. In our cheap motion control, we were lazy and used medium speed, so we just needed to tie down X0, tie up X1, and turn X2 on or off to change direction. In the real logic, they want to start out slow, so they need to do a tiny bit more work. For slow, X0 is on, but they need to modify both X1 and X2 to change direction. You can see that X2 works the same way as in our cheap design and is hooked to the Q output, but X1 is simply an inversion of X2. You remember from the paddle logic section that if one input is held high, a NAND gate acts as an inverter for the other input. Here it generates the inverted X1. X0 and X1 go through more logic to make them into CX0 and CX1, but for now we'll hook them directly to the X counter load pins. Let's stop talking and turn this on. And voila! Slow, bouncy ball. Let's try out the SBD signal. We'll wait for the ball to move away from the player. Bam! Reverses direction. Bam! Does nothing when already moving towards the player. Let's go put up a fake brick wall to test the brick hit line. The real wall is on the left side somewhere, but let's just put it here where 128 Henry and 32 Henry are off, and 64 Henry and 16 Henry are on. We'll hook these up to a spare 7430 using a couple of 7404 inverters. We'll keep it out of VSync and drop it on the video bus. Fire that up. Another exciting bar. At least this one's fat. And the ball goes right through it. The logic to generate a test brick hit signal is a bit more complex. Yes, we'll check that the ball hits the wall, but this simple logic traps the ball as you see here. This is because our fake bricks are not extinguished when hit, and since the ball sits in the same X spot for multiple lines, it oscillates direction every line. We need to modify this so that brick hit only rises once when hit. To fix this, we'll use another latch and only allow it to be set when brick hit is off. We then reset the latch when the ball hits either the paddle or the top boundary. This also has the nice side effect of only allowing a single brick hit until the ball bounces back off the paddle or top. I temporarily wired this up here. Bounces off the fake wall. Allow the ball to go through and turn it back on. Bounces off the back. Well, here's a stupid idea. Let's pretend our fake wall is one large brick and only display it when brick hit is off. Should disappear when hit and reappear when the ball hits the paddle or back wall. Kinda stupid, but fun to try. The X0 signal is generated by the volley counter, so let's go there next. We'll need a new 7408 in Dog 6 and a new 74193 in Baker 5. We'll also use another NAND gate in Baker 6 and 2 inverters in Charlie 5. You can see that the counter is reset when waiting to serve, and it counts up every time the ball direction switches towards the top boundary. This happens when the ball hits the paddle or hits the back side of a brick. The counter's A and B outputs are unused, The inverted C output generates X0, and the inverted D output generates V slow, which is used in the Y motion control. The counter is reset when you're waiting to serve, bringing up X0 and V slow. After 4 volleys, the counter hits 4 and X0 drops. When the counter hits 8, X0 rises and V slow drops. And when the counter hits 12, both X0 and V slow are low. At this point, the C and D outputs are high, preventing further stepping until the counter is reset before the next serve. If we map this out for the X direction, the ball moves slowly until the 4th volley, then speeds up to medium. On the 8th volley, it slows down again, and on the 12th volley, it goes back to medium. Seems like a strange pattern, but we'll see in a bit that they slow down the X motion and switch to medium on the Y axis at volley 8. Then at 12, they crank X back up to medium. I'll add a hex display to this counter and we'll turn this on. Slow. Changes to medium at 4. Slow again at 8. And medium again at 12. And stays there as predicted. Let's bounce this off the top of the bricks. Turn on the bricks. Slow. Medium. Slow. Medium. And stays there. Last note for this section, this speed up line on the volley counter loads all 1s when dropped. This input is asynchronous, so it happens immediately. It doesn't load to a 12, but has the same result since only the C and D outputs are used. The SU line comes out of the speed up section, so let's hit that next. Pardon the pun. We'll use an AND gate from Henry 2, the other latch from Dog 5, 2 exclusive OR gates from Charlie 6, and an AND gate from Dog 6. This latch is reset when you're waiting to serve, and it's set when a higher value brick in the back half of the wall is hit. This causes the SU line to drop, maxing out the volley counter, giving minimum speed. The rest of this circuitry then adjusts the raw X0 and X1 lines to generate the proper CX0 and CX1 bias value lines for fast speed. To change from medium to fast, we need to invert X0, which is done by this exclusive OR gate. X1 must also be flipped, but only when the ball is moving towards the player, which is done by these 2 gates. We finally have our proper CX0 and CX1 lines and can test the speed-up logic. We only have 1 huge fake brick, so we'll pretend it's a high-value one. Let the ball bounce a few times. Turn on the brick. And speeds up to fast when hit. Should also work when we hit the brick from the back. We've finally made it through the X motion controls, but I had another thought. Sorry. Since there's 3 load signals that generate 6 distinct speeds, we can use a 3 to 8 decoder to drive 6 LEDs to show us the speed and direction. We only need 1 current limiting resistor here because only 1 output is on at a time. I whipped up this meatball display with decoders and LEDs for each axis. The left LEDs show slow, medium, and fast speeds towards the top boundary, and the right LEDs show motion towards the paddle. We'll use the Y LEDs later. I also added an LED that shows when SU turns on, and move the volley counter so we can hopefully capture everything at the same time. I'll turn on the fake brick wall so this doesn't take as long, but I'll disable the brick hit line for now. We can see the ball moving slowly for the first 4 volleys, medium for the next 4, slow again, and finally settles on medium. I'll re-enable brick hit, and when hit, SU asserts maxing out the volley counter, and the speed up logic emits load bias values for fast motion. This will remain fast until the next serve. Let's build the final section for today. We'll need a new 7474 in Able 6. We'll use 3 gates from Able 5, 1 gate from Charlie 6, 1 gate from Charlie 4, 2 gates from Baker 6, and 1 inverter from Charlie 5. This bottom flip latch handles the vertical direction, while the top latch and rest of the circuit handles the speed. The bottom latch is wired differently than how we did it. Instead of checking the left and right sides independently, they just check when the ball runs into V-Sync and use this to clock in the 16 Victor Prime line. 16 Victor Prime is off when the ball hits V-Sync at the bottom of the screen, so this resets the latch. And 16 Victor Prime is on when the ball hits V-Sync at the top of the screen, setting the latch. The inverted output then drives the Y2 load input directly. Note that since they're using V-Sync instead of the sides, the ball will overlap the left side briefly in normal mode and overlap both sides for just 2 lines when player 2 is up on a cocktail model. Something you probably wouldn't notice unless you're really looking for it. In part 7 we showed how the PC and PD lines are generated by the paddle size counter and also showed this reflection chart. You can see the top latch is clocked from a ball paddle hit, and that the bottom latch set and reset lines are affected by a hit. If we look at the bottom first, the PD line is on when the ball hits the bottom half of the paddle, so the latch gets set and the ball will travel downward. And if the ball hits the top of the paddle, the latch is reset and the ball travels upward. For the upper latch, the output of this exclusive OR gate is on when only one of PC or PD is on. So this latch is set when the ball hits the center and is reset when the ball hits either outer edge. The rest of this logic adjusts the speed. You'll notice that there are no resets in this section, so the Y motion latches will retain some state. If we plot this out, on serve, both the top and bottom latches will be whatever they were, and V-slow will be high. So the ball's vertical direction will be up or down, depending on the state of the bottom latch, and the ball's vertical speed will be slow or medium, depending on the state of the upper latch. If the ball hits the top half of the paddle, the bottom latch resets and the ball moves up, and if the ball hits the bottom half of the paddle, the bottom latch is set and the ball moves down. If the ball hits the center portion of the paddle, the top latch is set and the vertical motion is slow. And if the ball hits the outer edge, the top latch is reset and the ball moves medium. Now when V-slow turns off on the 8th volley, or when a speed up occurs, this combinatorial logic ignores the top latch and only emits fast speeds. The player therefore can only use different paddle hit bank angles for the first 8 volleys and before hitting a high value brick, After that, the vertical motion remains fast until the next serve. One more note on this. If you hit the top boundary, you get a small paddle, and all of the logic we discussed here still works, just on a smaller footprint. Let's check out our Y motion work. I hooked up the Y-axis LEDs on our meatball display and freezed X motion so we can test the basic direction changes first. Testing here is a little challenging since we're not hitting the paddle yet, but we can manually change a few things. I've already set the top latch, giving us slow speed, and resetting the latch gives us medium. We can toggle between those as if we hit the paddle center and outer edges. If you look closely, you can see that the ball goes through the left side and hits V-sync before changing direction, and it's brighter where they merge, as predicted. To get fast speed, V-slow needs to be off. You remember that V-slow comes from the volley counter's D output when the counter reaches 8, but since we're not moving horizontally, the volley counter doesn't step. We could switch the counter clock to the Y2 output, but the easiest thing to do here is just trip the speed up latch, which turns off V-slow. Vertical motion now stays fast, even if I set and reset the top latch. Final test is to turn X motion back on, force large paddle, turn off attract mode, and hit the paddle. We can see that this is basically working. And after the 8th volley, vertical motion is fast. I'm going to disable stepping of the volley counter so we can capture the 4 different reflection angles. Top outer edge, medium up. Top center, slow up. Bottom center, slow down. Bottom edge, fast down. Allow paddle size to change when hitting the back wall, and we get the small paddle. You can try capturing these various reflection scenarios yourself. I'm tired. Final quick test for flip screen. Seems like everything is working nominally. Let's chuck this stuff into our retro schematic. Before we get started, I mentioned that the raw ball signal goes through other stuff, specifically the game state logic, and it comes out on this ball display line. But I never showed how we get B-Sync. B-Sync is just a copy of ball display synchronized to the clock in Jack 1, then dropped on the video bus. Interesting that this line is also used in other logic. You would think you would want some isolation from potential interference from other things on the bus, but once again, it works. We'll start by creating our own 74193 symbol, kind of like the ones on the legacy schematics. drop in all the gates we'll need. Rename everything. And wire it up. Add that resistor. Looks like a winner. That's way overboard for today, so get some rest and I'll see you in the next part. We'll be hitting the bricks. Thanks for watching.